In this lesson, we're going to continue to focus on enthalpy. So remember that is the delta H value. Sorry about my cat. That's the delta H value, and it's the change in heat over the course of the reaction. So in the last lesson, we saw that we could calculate that using the bond energy values for the reactants and the products. So we're going to look at 3 more ways to calculate that in this lesson using something called calorimetry, Hess's law, and the enthalpies of formation. Now, calorimetry is really the only way that we have in the lab to find the enthalpy value. And so we'll focus on that and hopefully have time to do that in the lab or through a lab simulation. And then Hess's law and the enthalpies of formation, and also what we saw last time with the bond energies, those are going to be paper and pencil calculations using charts. All right, so first let's talk about calorimetry. Calorimetry, that vocabulary word, means the measure of heat transfer. So it's a means that we have to measure how much heat moves from one place to another. A calorimeter, to be more specific, is the device that we use to do that. So when we're looking at how much heat is flowing from one place to another, we can't measure the heat flow. Instead, we have to measure what was the temperature before and what was the temperature after, and then we can use that to calculate the heat transfer. Remember that heat is the total for a system and temperature is an average. So temperature will be combined with some other factors to find the heat transfer. But there's no heatometer, so to speak. There's a thermometer, so we can measure temperature and then we can relate that to the heat. How does calorimetry work? Well, first of all, we need to know the specific heat capacity of the material that we're using. And this is called C in our equation. But it is specific to a material, okay? And that's very important to know. The specific heat capacity is specific to that material. So water's specific heat capacity doesn't change. Iron's specific heat capacity doesn't change. It is the amount of heat that would be required to raise the temperature of that substance, if you had 1 gram of it, to raise it by 1 Kelvin or 1 degree Celsius. It's the amount of heat required to raise the temperature. So if that value is large, like it is for water, it's going to take a lot of heat to raise the temperature of that substance. But if the value is small, like it is for iron, if you see that it's almost 1/10 of what water's is, it's going to take much less heat to raise the temperature of that substance. So this is important to note when we're looking at a heat transfer experiment. If the same amount of heat leaves iron and goes to water, for example, if you have a really hot piece of iron and you put it in water, water's temperature is not going to change that much, and iron's temperature is going to change a lot because the value for iron is much smaller, so it takes a lot less heat to adjust the temperature. And water's value is large, so it takes a lot of heat to adjust the temperature. We can relate this to the very pleasant temperatures that we find at the beach. The water that's there is helping to keep those temperatures pretty steady because it absorbs and releases heat very slowly. On the other hand, if you put an iron pan on the stove, it's going to heat up very quickly. All right, so when we're doing calorimetry, we keep that in mind, the specific heat capacity of the substance, and that goes in the C value. And our equation is Q, which stands for heat, equals mc delta T. M is going to be the mass, specific heat is going to be a value for that substance, and then we'll look at the temperature change. Most of the time when we're doing calorimetry experiments, we have 2 different substances, so we have to be very careful. Whatever substance we put the C value for here, that is the mass that we have to use, the mass of that substance. And the temperature change has to be for that substance, and we'll be finding the heat for that substance. So in calorimetry experiments, just keep in mind that C goes with a substance and the rest of our values should be related to that substance as well. This is what our lab calorimeters are going to look like. Now, if you were using what is called an ideal calorimeter, it's going to look a lot different from this. It's going to be a lot more insulated. But in the lab, we're just going to use a coffee cup most of the time. And we'll put a lid on it to try to keep the heat from escaping if we're producing heat, and try to keep any extra heat from coming in if we're not producing heat. We need something to stir the solution with just to make sure everything gets mixed in good when we're doing our experiments. So we can use any kind of stir stick, and we'll stick that through the lid. And then we'll need a thermometer as well, of course, because the temperature change is going to kind of reveal the heat transfer. You can use your thermometer as your stir stick as well, and then you can just have that one hole in the lid. That's one way you can kind of simplify a calorimetry experiment. So your reaction is going to be going on in here in the solution, and then you will consider everything outside of that to be your surroundings. So the purpose of the lid on the coffee cup is to kind of ignore everything else that's going on out here, and we can just focus on what's going on in the cup, and that can be our system and our surroundings, and we don't have to consider, like we talked about before, the entire universe. But there is going to be some heat that's just inevitably going to be lost, even if it's just a tiny hole in the top of the cup, or even the cup itself can absorb some heat, and so we'll have to take that into consideration when we look at our results. When we're doing these coffee cup calorimetry experiments, we're going to use the solution as the basis for our calculations. So we're going to be calculating the Q for the solution. And normally we'll just be talking about water. So we'll have the mass of the solution, which is mainly going to be water. So our mass is mostly consisted of water. And then we'll have the specific heat value, and it will normally be the same as water unless we have a lot of solute in our solution. And then we'll be looking at the temperature change again of the solution. So the final temperature minus the initial temperature. And when we find Q, it'll be the heat that was lost or gained by the solution, not by the reaction itself. So the reaction is giving this heat to the solution or taking the heat from the solution, but the heat that we're calculating is actually the solution's heat. So we'll need to relate that to the experiment somehow. Okay, so let me clarify that again. When we're doing these coffee cup calorimetry experiments, we've got some reaction going on in the water. And what we're measuring is the heat that is lost or gained by the water or the solution. And we have to relate that back to the reaction, because we can't get in the reaction and measure its mass. That makes sense. Or its temperature change. The temperature that we're measuring when we stick the thermometer in there is the temperature of the solution. So we're finding the heat of the solution itself. Maybe these points will kind of help to clarify that. The reactants and the products, those are the system. But the water in which they're dissolved in, that's the surroundings. And that's what we're calculating Q for. So when we find Q, we're finding the Q not for the system, but for this, the surroundings. However, the heat that is lost or gained by the solution is equal to the heat lost or gained by the reaction, but it's going to be opposite in sign. So when we find that the solution, let's say it gained 568 joules of heat, that means the reaction must have lost that heat. So when we calculate Q for the solution, to find Q for the reaction is simple. We just flip the sign. And we keep in mind that if the solution is gaining the heat, the reaction or the system must be losing it. So that's exothermic. However, if the solution lost heat, that must mean the reaction or the system gained it, and so that would be endothermic. So when we find Q for the solution, we'll need to flip the sign to see the Q for the reaction. Right, here is an example. We have a 97-gram iron bar, and it was heated to 143 degrees Celsius and placed in a coffee cup calorimeter with 350 grams of water, and the water is at 25 degrees Celsius. The maximum temperature of the water was measured to be 28.4. So let's think about what's happening. We have a beaker of water, it's quite a bit of water, 350 grams. And the water is at 25 degrees Celsius, and that's just room temperature. And then we have a 97 gram iron bar, and it is heated to a really high temperature, 143 degrees Celsius. So you got a hot piece of iron, and you're placing it in room temperature water. So of course the water is going to warm up. And this is the highest temperature reached by the water. So the water is going from 25 to 28.4. So the first question is, how much heat was gained by the water? Remember that heat is Q. And if we're talking about a calorimetry experiment, we're going to use that Q equals mc delta T to find Q. The second question is, how much heat was lost by the iron bar? Well, we know that the heat gained by the water came from somewhere. Well, where did it come from? It came from the iron bar. So the heat gained by the water is equal to the heat lost by the iron bar. So it'll just be negative whatever we find for Q. And then the last question is, what is the specific heat of iron? And that's our C value. If we know Q for iron, then we can use it to find the C value for the iron, along with the rest of the data that we have here. So let's start by calculating how much heat was gained by the water. So we have our equation, Q equals mc delta T. What was the mass of our water? If we're doing the Q for water, we need the mass of the water. Well, it's 350 grams. We know from the previous slide that the specific heat of water never changes. It's 4.184 joules per gram degree Celsius. And then our temperature change is always going to be the final temperature minus the initial. So we'll subtract those two values. Notice your units here. Your grams can cancel, and your degrees Celsius will cancel. So you'll be left with joules, which is a unit for energy, and heat is a form of energy. So calculating that out, we find that the water gained around 5,000 joules of energy. Now I know the water gained that because its temperature went up, so its sign is positive. So how much heat was lost by the iron bar? Well, if the water gained that much heat, it came from the iron bar. So the Q for the iron is simply the opposite of the Q for the water. So whenever we find Q for the solution or for the water, depending on what type of experiment we're doing, the Q for the opposite thing, the system, in this case the iron, is going to have the opposite sign. The next question is, what is the specific heat of iron? So we'll use our Q equals MCAT equation again and kind of plug in what we know. Let's first rearrange to solve for C, because that's specific heat. So the specific heat is going to be equal to our Q value divided by our mass times our temperature change. The Q value we just found for iron to be that negative 4,979 joules. The mass of the iron is 97 grams. And the temperature change for the iron, let's look at how they found this. Here's the initial temperature of the iron. And this final temperature is the same as the final temperature for the water. Remember that when two things come in contact with each other that have different temperatures, the temperature is going to regulate until it reaches an equilibrium. And they told us that the final temperature of the water was 28.4. So that must also mean the final temperature of the iron is 28.4. So we'll subtract those two. Notice the iron's temperature changed a lot, whereas the water's temperature changed only about 3 degrees. And we'll see why when we calculate C. Okay, so put these values in, and we see the C value for the iron is 0.45 joules per gram degree Celsius. Notice how much smaller that is than the C value for water. And that is the reason why the iron's temperature changes so much, because it has a really low specific heat compared to water, which has a high specific heat and its temperature changed only a little bit. The key, though, is that the same amount of heat was transferred, but the temperature change was not the same for both of them, because temperature is not heat. Temperature is not heat. Heat, in water, we can have the same amount of heat and be only changing by 3 degrees, whereas iron, we're changing by 100 and something degrees, but it's the same amount of heat. So keep that in mind. Heat is not temperature. All right, another experiment. We have 20 milliliters of sodium chloride at 1 molarity, and it's at 22 degrees Celsius. And we mix it with some silver nitrate, and it's in the exact same proportions at the same temperature. When we do that, a white precipitate forms. Remember, that's when a solid forms when you mix two ionic compounds, because those ions prefer to be together instead of separated in the water. The temperature when that happens reaches 29.6 degrees. So notice we started off with both of them at 22, and now they're at 29.6. So the temperature went up. That tells us that the reaction is exothermic, that the reaction is giving heat to the water. We're going to assume the specific heat capacity of the mixture is this, and the density is 1 gram per milliliter. And we'll assume that the volumes are additive. That just means that the 20 and 20 equals 40 milliliters. So we've got 40 milliliters, which, if this is the density, 1 gram per milliliter, that's 40 grams. We have our initial temperature and our final temperature and our specific heat. So we should be able to calculate Q. Okay? All right? But that's not what they ask us to do first. They first want us to write the net ionic equation. So I love the way they just keep getting us to review things that we've learned before. What is the net ionic equation for sodium chloride and silver nitrate? So we'll look at that. And then they want us to calculate delta H. Notice they're not asking me to find Q. But I know I need to find Q if I'm doing a calorimetry experiment. Anytime you see this calorimeter word, you've got to think Q. So there's got to be a way to get from Q to delta H. So we'll look at that. All right, first off, let's look at our net ionic equation. Okay, and it just popped up, but let's figure out how they got there. We have sodium chloride. See if I can type. Sodium chloride and silver nitrate. Anytime you have two ionic compounds mixing, you're going to do a double replacement or a partner swap. So we're going to make sodium nitrate and silver chloride. Now if we think back to our solubility rules, we know that group 1 elements are soluble in ionic compounds. So this sodium chloride would break apart. We also know that nitrates are always soluble. So the silver nitrate would break apart. On the product side, the sodium nitrate has group 1 and nitrate, so it would definitely break apart. And then we have silver chloride, and that's going to be our precipitate. We know there is a precipitate because it told us so, and we know it can't be the sodium nitrate, so it must be the silver chloride. So the sodium nitrate, those components are soluble on both sides, so they're going to be spectators. So we'll just be left with the silver and the chloride forming the silver chloride. And those two would be in the ionic form on the left-hand side, and then the solid form on the product side. So there's what our balanced net ionic equation would look like. Alright, now let's move on to calculating delta H. Now, as I said before, to calculate delta H, we've got to find Q first. And we'll start by finding the Q, or the heat for the solution, because that's what we have the C value for. So Q equals MC delta T. Now for the mass of the solution, we have those two 20 milliliters that were added together. So that would be 40 milliliters. And it said the density was 1 gram per milliliter. So that must be 40 grams. We then have the specific heat given to us, and we know the temperature changed from 22 to 29.6. So there's our temperature change. So we have M, C, and delta T, and we'll multiply those together to find the Q of the solution. And we find that the heat of the solution is positive 1,270 joules. That means the solution gained that heat, right? Because the temperature went up. But where did that heat come from? It had to come from somewhere. In this case, it came from the reaction. In the previous example, remember, it came from the iron. But in this example, it's coming from the reaction. So the Q for the reaction is just opposite in sign. The reaction is exothermic because it's giving the heat to the water. And that's why we're coming up with a negative Q value for the reaction. Now to calculate delta H, remember, is the heat per mole. So in order to find delta H, we need to know Q, and then we need to know the moles. So the first thing we want to do is find the moles of either of our reactants. The reason that we can use either of them is because they were in equal amounts, if you'll recall. We had 20 milliliters of both, and they were at the same concentration. So we'll use that to find our moles. We had 20 milliliters, that's 0.02 liters, and it was 1 molarity. Remember, molarity is moles per liter. So that means that I must have 0.0200 moles of silver. Okay, this value in the middle, this conversion factor, is coming from that 1 molarity, because molarity is moles over liters, so our liters will cancel. So we have this many moles of silver. We also have that many moles of chloride. From there, we can find the delta H. So it's Q per mole. Now the mole part is ultimately for the silver chloride, but that's going to be the same as the silver or the chloride if you think about your stoichiometry. So that's why they told us that we could find either one of those. So we plug in our Q for the reaction, which was negative, and then we plug in our moles, and we divide. Now delta H is usually going to be in kilojoules per mole. So when you calculate it, you'll notice that it's a very large number. If you're talking about joules per mole, we'll usually divide that by 1,000 and report delta H in kilojoules per mole. So how is Q different from delta H? The Q value tells us the heat that was lost or gained in that experiment in that calorimeter. If you change those conditions, you could get a different Q value. So it's for a specific experiment. However, the delta H value shows us the heat lost or gained in the balanced equation. So someone else could go and do the same experiment and they should get the same delta H value. They could use a different amount of salt, a different amount of water, and they should get the same delta H value because the delta H value is related to the balanced chemical equation. And as long as they're doing that reaction that corresponds to that chemical equation, then delta H will stay the same. But the Q value is for that specific parameters in the calorimeter, how much heat was lost or gained. Right, one thing that I want to go back and just make sure that I clarify is this per mole. What do we put on the bottom when we're calculating delta H? All right, so I got a few notes for you here. When you do the per mole, this is known as per mole of reaction. So you need to choose something that has a coefficient of 1 in the balanced equation. Okay, that's your first note when you're doing the per mole. If nothing has a coefficient of 1, or if the thing you're choosing doesn't, then divide by the coefficient. All right, the second note. If you have more than one reactant that you're talking about, you're going to use the limiting reactant in your per mole. Okay, so two things to consider. It's called the per mole of the reaction. So you want to choose something that has a coefficient of 1. And then if you have more than one reactant and they're in different amounts, the silver and the chloride were the same amount, so that was such a blessing because we didn't have to worry about the limiting reactant. But if you have them in different amounts, then you've got to find the limiting reactant and you're going to use that one. And if its coefficient is not 1, then divide by its coefficient. Okay, I'll try to pull some examples where we'll have to use those rules and figure out what we do for per mole. And please bring any questions you have about that. All right, we'll pick up from there next time with 2 more ways to calculate delta H.